Okay, so do you have any questions before we continue? Now, I had one mistake in our last lecture. So let's first discuss that mistake. Now, if you remember, we were discussing the relativistic corrections, and we said that H prime for the first relativistic correction was minus 1 over 8 m squared c cubed p to the 4. And then, since H0 was p squared over 2m plus v, we said that the p squared acting on our eigenstates was just 2m times e minus v acting on our state. And then in the book it says that p to the 4 NLM, the matrix element of this one, is equal to 2m e minus v squared times NLM. And we said that there was something wrong here because p squared does not commute with p squared doesn't commute with v, so p squared 2m e minus v NLM is not equal to 2m e minus v p squared acting on NLM, which is 2m e minus v squared acting on this state. This is not true. But at first sight, it looks that in writing this expression, this is what the book seems to be using. And we said that this doesn't work because p squared e minus v, they do not commute as operators. Yep. But we can also write this matrix element, p to the 4 NLM, is nothing but p squared NLM norm squared. Or we can think of it as NLM p squared acting on the left, p squared NLM acting on the right. So although this relation, this non-equality is still true, so that argument is correct, but when it comes to the matrix elements, it doesn't make any difference. So let's also see how it come. How come, although there is no such equality, the matrix element of p to the 4 satisfy that relation. So let's see. Let's look at p squared acting on 2m e minus v acting on this state. Now I can write this as 2m e minus v times p squared acting on NLM plus their commutator. Acting on NLM. So somehow this last term should have a zero overlap with the state NLM. So we should show that NLM and this commutator should be 0. Now let's evaluate the commutator first, and let's evaluate the commutator. Well, E is just a constant, so we can just forget about that. It commutes. This is minus 2m p squared and the commutator of v, which we can write as p scalar product with the commutator with v plus scalar product with b. So what is this commutator? V is our potential, is a function of x. Well, you can just derive it. Let's say this commutator acting on some arbitrary function. This is p acting on v psi. minus V times P acting on psi. What's P acting on a function of x? Derivative times minus I h bar times the gradient acting on V psi, minus V times minus I h bar the gradient acting on psi. In the first term, we can just use the chain rule. Minus I h bar gradient acting on V psi plus V times minus I h bar gradient of psi minus V times minus I h bar gradient of psi. So all these last terms cancel. So in general, P acting P and V commutative any function of x. I mean, V, although we will be assuming that it is the potential of the proton, but this is true for any function of position. This commutator is equal to minus I h bar gradient of V. Just a function of x. So, okay, we know this commutator, so that basically tells us that this P squared 2m E minus V, this commutator is equal to minus 2m P scalar product minus I h bar gradient of V plus minus I h bar gradient of V dot P. Now that gradient is acting only on V and P is acting on everything that is on its right. Well, I can do the same trick again and just move this P to the right so that the first term and the second term, they will become similar. Well, okay, you don't see the and. Okay. So the first line and the second term becomes similar, so that might simplify my life. So this is equal to minus 2m twice minus I h bar gradient of V dot P plus minus I h bar the commutator of P and gradient of V, but we had just calculated that the P commutator with any function is the gradient or the divergence of that function. So this is equal to minus 2m minus 2I h bar gradient of V scalar product with the momentum plus minus I h bar squared times the Laplacian of V. Now we know that in our special case at least V is equal to Q over 4 Q minus E squared 4 pi epsilon 0 1 over R gradient of V what's the gradient of V? So V is the electrostatic potential if you forget one of the factors of E. So what's the electric field of a point charge? E squared minus E squared over 4 pi epsilon 0. It's in the radial direction divided by R squared. Laplacian of V let's remember your electromagnetics course. Laplacian of the electrostatic potential is charge density over epsilon 0. So here we have a point charge at origin. So charge density is Dirac delta R over epsilon 0, while the charge multiplied by E squared. Well, this is not the potential, this is the potential energy, which is just the potential multiplied by the charge of the electron. So there's a minus sign. So now we have the final result that this commutator is equal to minus 2m minus 2I h bar times minus e squared over 4 pi epsilon 0 r hat dot p divided by r squared. Well, let me write it this way, they don't commute. And plus minus I h bar squared minus e squared divided by epsilon 0 Dirac delta of r. This is the three-dimensional Dirac delta. Now we need to calculate the matrix element of that thing. Now let us start with the first term. So if you forget about the constants, NLM r hat over r squared dot p, this is equal to d cubed r. We have psi NLM conjugate. Well, p is the gradient operator, and we are only taking the radial part of the gradient operator. So it is 1 over r squared, the radial part of the gradient operator. D over dr, that's the easiest part. D over dr. Psi NLM r. Now we can of course separate the angular part and the radial part. You see that the angle, there is no operator that's acting on the angles, so I can just integrate over the angular part. They are properly normalized, and that leaves me only with the radial part, dr from 0 to infinity r squared. The radial part depends on the quantum numbers n and l. 1 over r squared d over dr, r and l. I don't write the complex conjugate anymore because the radial part is real. Well, this is nice. The r squares cancel. So what I am left with is 1 over 2 r and lr squared evaluated at r is equal from 0 to infinity. Well, at infinity, my wave function is 0 anyway. There is no contribution. And there is a single contribution. There might be a contribution only from r is equal to 0. This is the matrix element. Well, we also know one thing. Do you know how the radial function behaves as r goes to 0? Do you remember the asymptotics? This is r to the l. Now, if you remember the radial equation would be minus h bar squared over 2m 1 over r squared d by dr r squared d by dr minus or plus now minus h bar squared over 2m l plus 1 over r squared. So at r is equal to 0, now if we have, let's say for example for the hydrogen case, the potential is 1 over r. As r goes to 0, the important term is not the potential, but this r squared piece. And the matrix element of that piece, unless L is equal to 0, diverges. Unless it is cancelled by the first term. So it has to be cancelled by the first term to get a finite kinetic energy. And that leads to the condition that as the r goes to 0, the radial function should go to 0 as r to the power L. Or else it wouldn't do. But if this is satisfied, then this matrix element would be 0 if L is not equal to 0. So we don't need to worry about this matrix element if L is non-zero. Only for the L equal to 0 case we need to worry. But let's look at the other term, this one. We have this Dirac delta piece. This piece. NLM, Dirac delta cubed R, NLM. Well, kind of this is the easiest piece. You can just take the integral using the Dirac delta. And this is nothing but psi NLM 0 squared. And again, this is automatically 0 if L is not equal to 0. So we had this correction to our relation if we try to commute to p squared and e minus v. They don't commute, but they are proportional to this term, the commutator. But the matrix element of the commutator for the eigenstates are 0 if L is not equal to 0, because both of the terms over here, both this one and this one, it gives 0 in their matrix elements, in their diagonal matrix elements. The only case you have to pay attention to is what happens when L is not equal to 0. Well, that is also not so difficult. When L is not equal to 0, we have two contributions. One from here. If L is not equal to 0, then we have this NLM R hat over R squared dot P matrix element. We had evaluated it above. It was 1 over 2 R NL squared, etc. Well, this one. This is equal to minus 1 over 2 R. Well, L is 0, M is 0 now. Zero, 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 and 0, 0 squared. Now, if we look at the Dirac delta one, and 0, 0, Dirac delta cube, or and 0, 0, this will be equal to R and 0 at 0, Y LM. Well, when R is equal to 0, you can actually take any number, any angle. Y00 is a constant anyway, squared. This is equal to R and 0, 0 squared. So do you remember what is Y00? Yeah, that's the easiest one to remember. It's a constant. Furthermore, we know that it is normalized. This should be 1. It's a constant. D omega is 1. D omega is 4 pi. Y00 is equal to 1 over square root of 4 pi. Here we have the Y00 absolute squared, so that is just 1 over 4 pi. Well, let's go back to our matrix element. We need to calculate the matrix element of this thing. Well, for L is equal to 0, from the Dirac delta, we get the 1 over 4 pi, the matrix element of the Dirac delta. So we have the 1 over 4 pi epsilon in both terms. E squared is common in both terms. And the matrix element of Rp, there is something we had forgotten over there. It has the minus I h bar. This is P. So from the matrix element of P, we have an additional h bar, and we have this additional 1 over 2 term. So it will cancel this 1 over 2, and both of the terms will cancel each other. So the matrix element will be 0, even for the L equal to 0 case. L non-equal to 0 case, each one of these terms, the matrix element is 0. For the L equal to 0 case, the matrix element of each one of the terms is non-zero, but nevertheless their sum just gives 0, so that's why it works. You can just in the matrix elements that we are considering, you can just ignore this commutator. Okay, any questions? Anything you want repeated? Well, one difficulty is that I don't want to go over all the solutions of the hydrogen atom, but it's also natural that you have forgotten all the solutions of the hydrogen atom after 1 year. So if you have any questions about the hydrogen, please ask. We will not be needing all the wave functions, etc., but some of the properties, like how it behaves at small distances, that at small distances the wave function goes as r to the L. This is independent of the potential, in fact, because as there is this term, as long as your potential doesn't diverge faster than 1 over r squared, then the radial function should behave like r to the L, whatever your potential is. Not just only the hydrogen atom. Okay, so let's continue trying to calculating the other corrections to the spectrum. We had already calculated the correction, the relativistic corrections. Let me write the full expression of the relativistic correction. ER, the first correction relative to the energy, N, is equal to minus En over MC squared times 1 over 2 4n divided by L plus 1/2 minus 3. So one thing that this did was it lifted the degeneracies between different L values, because before this correction the energy only depended on N, it didn't depend on L. For a given N, L can take different values and you have the degeneracy. And this relativistic correction just lifts it. Another observation is that this correction is proportional to energy over MC squared, which we said that En over MC squared is around 10 to the power minus 5. This is a small correction. Just to give you an idea, do you know what is the energy corresponding to room temperature? How many electron volts?
25 electrons.
At room temperature, KT is 1 over 40 electron volts. What you say? So if you compare the room temperature energy to this shift, so KT over ER1 let's calculate the first correction. ER1 is something like 10 to the power minus 5. En is of the order of 10 electron volts. So the first correction is of the order of 10 to the power minus 4 electron volts. And the room temperature divided by KT is something like 10 to the power minus 4 electron volts divided by 1 over 40 electron volts. This is something like 10 to the power minus 2. Now, why is this important? What the room temperature will do is it will just cause the atoms to the hydrogen. It will be vibrating. And the typical energy of vibration will be 1 over 40 electron volts. Well, that will just shift the energies. That will cause some Doppler shift, because the source of the radiation is moving with a given energy. Due to this Doppler shift, the radiation that you observe will be shifted from the exact values that we evaluate. And that the amount of shift will be typically of the order of 1 over 40 electron volts. And 1 over 40 electron volts is already much larger than this correction. So this correction, this is a fine structure. Correction is much smaller than the correction due to the thermal motion. This is typically what you would expect from these order of magnitude arguments. So it's difficult to observe it at room temperature. You have to cool the system if you want to observe this shift. Because the lines will be already, due to this random motion, you will observe that some of the lines the frequencies will be shifted up, some of them will be shifted down because the atoms are moving in random directions. So the line shape you observe will not be a mathematical line, but it will have a width. The width will be of the order of 1 over 40 electron volt. And this shift is already smaller than that width. So you won't be able to observe it within that width, the shift. Now let's look at some other correction. Now let's just imagine that you are an electron. What do you know about the electron? And what do you know? Its name is electron. It's charged. Good. Do you know what the electron means? Have you ever seen an electron? I'm sure you did. It's a Greek word for amber. So you have seen an electron. I mean, the first experiments on electricity was done using amber, so that's where the name comes from. So it's charged. What else do you know about the electron? It has a mass. Okay, good. What else? It has a spin. So classically, we can just model the spin as a rotating sphere, right? Well, so we have an electron, which if you model it as a rotating sphere, it also has a charge. So we have a charged sphere that is rotating. So it has a magnetic moment. So that is one thing. Electron should have a magnetic moment. And let's look at the hydrogen. Just imagine that you are the electron. And what do you see around you? There's proton moving around. So there's a charged object moving around. It will create a magnetic field. Well, you have a magnetic dipole moment. There is a magnetic field in the environment. So there will be a correction to your energy. This is mu of the electron, the magnetic dipole moment of the electron, and B is the magnetic field created by the proton. Well, this is mainly why we call it the spin-orbit coupling, because the magnetic dipole moment of the electron will be related to its spin, and the magnetic moment created by the proton will be due to its motion, relative motion with respect to the electron, while that will be the orbital motion of the electron. So let's try to estimate what they are. Let's look at the magnetic dipole moment. Well, it's the property of the electron itself, not of the hydrogen atom or the electron in the hydrogen atom. So we should be able to express it in terms of other properties of the electron. Furthermore, it's a vector. So the only other vector we have is the spin of the electron. So the magnetic dipole moment should be proportional to the spin of the electron. There is no other possibility. So let's do some dimensional analysis. What is the dimension of mu e? Magnetic dipole moment. Do you remember the magnetic dipole moment? Coulomb meters. No, ampere meter squared. So you see, in classical electrodynamics, So if you remember your 105 or 106 or 110 courses, if you have such a loop carrying a current I, the magnetic dipole moment is defined as I times the area. So the unit of the magnetic dipole moment will be ampere, which is coulomb per unit time, coulomb per second. Area is meter squared. Now, what is the unit of the spin? Joule second, or kilogram meter squared per second. So let's see, what's the unit of this constant A? Something we don't know yet. We are trying to identify what A is. So the unit of A will be the coulomb per second meter squared divided by kilogram meter squared per second. Well, meter squares cancel, seconds cancel, so it should be coulomb per second. Kilogram. Okay, so this A should again be written in terms of the properties of the electron, and its unit should be coulomb per kilogram, charge per mass. Well, the easiest guess will be mu E is Q over M times S, which, by the way, turns out to be the correct expression for the electron. Well, the more precise way of writing this is mu E is equal to Q over 2M. Let's put GE times S, where this GE is called the gyromagnetic ratio. Now we can make a classical argument that would tell us that the magnetic moment should be Q over 2M multiplied by the spin rather than Q over M. Now let's also go over that argument. Rather than taking the electron as a sphere, let's just assume that it's a ring. This is our electron. Not the orbit of the electron itself. So the current running through it will be the Q over T, the period of the rotation of the electron. The angular momentum, or the spin, would be just M R squared. This is I, and 2 pi over T. Do you agree?
So I don't understand. No. It is the electron is a ring?
Yes. No, there's
and
no.
it also spins around stuff.
No. I mean, what's an electron? We say that it's a point charge, but we don't actually know it. I mean, you can make models of electron, semi-classical models, in which you can model it as a sphere rotating around itself. Well, calculating the magnetic dipole moment of a sphere is kind of complicated, so what you do is you take the sphere, divide it into very small rings, and sum them up. So rather than summing them up, I'm just taking a single ring. Now the angular momentum is r cross p, so it will be m r times 2 pi r over t. So I over the mu is q over t times r squared, pi r squared, I times the area. Mu over s will be q over t pi r squared times t over 2 pi m r squared. t's will cancel, pi's will cancel, r squares will cancel, so it's q over 2m. If it was a classical object, the electron, then the relation between its magnetic dipole moment and angular momentum should be q over 2m, not just q over m. Dimensional argument doesn't give us these factors of 2, but the actual expression turns out to be q over 2m times the spin multiplied with a correction factor. Now this GE is equal to 2 if you take Dirac theory. From Dirac's equation, is equal to 2, I think it should be 2 alpha over 4 pi. This is the next correction. We can calculate it. And this is Nobel Prize for Schwinger. So I got the Nobel Prize for calculating that correction of over 4 pi. And nowadays we know this number up to, I think, 24 digits after the decimal point. We can also measure it experimentally up to 24 digits after the decimal point, and they agree with each other. Okay, so this is we know the magnetic dipole moment of an electron. So that was kind of the first part of our correction. So we have this one we know. Now let's look at the magnetic field created by the proton. This is the electron. Let's just consider the reference frame of the electron. Well, classically we can say that the proton is just revolving around it. So we can just think that there is an average current running through this ring, which is the charge of the proton divided by T. And what is the magnetic field created by this ring? So do you... Let's remember the Biot-Savart law. Do you remember it? dB is equal to mu 0 over 4 pi dl cross r hat over r squared times I. Do you remember it now? Okay, so let's see. Let's just take a very small segment over here. This is our dl. And this is our r. The direction of the L cross R, upward. This is equal to mu 0 over 4 pi charge of the proton divided by the period of rotation. dl cross r hat just gives me dl in the z direction. They are perpendicular to each other. dl cross divided by r squared. So dB is in the z direction. All the segments contribute equally. They all contribute in the same direction at the center. So I can just sum them up, and that would give me mu 0 over 4 pi q proton divided by T 2 pi r divided by r squared in the z direction. I can make cancellations to mu 0 over 2 r q proton divided by T in the z direction. What's the angular momentum? Well, the angular momentum of the electron. So we had already written it down. Now, this was the spin. It is again r squared 2 pi over t, which is also in the z direction. And so we see that the magnetic field created by the proton is in the same direction as the angular momentum of the electron. So we can just write them in terms of each other. So this will be equal to mu 0 over 2r cube proton L times 1 over 2 pi mr squared.
You consider the time of the rotation of the charges in the electron ring equal to the time of the rotation of the proton.
Okay, so there are two t's over here. There is this t over here, which is the time of rotation of the electron. But, I mean, the final result, this result, is independent of t. And then this t over here is not the rotation of the electron. This is the it's not neither the rotation of the proton around itself. It's the the orbital time. If this will make you happy, let's just put a prime over here.
When you made the substitution here, the t went into L.
You see, above here, this is not L. This is S. Spin. Okay, it is the angular momentum of the rotation of the electron around itself. That is what we call spin. Here, this is the rotation of the electron around the proton. So that is why this is T prime. And when I write the B in terms of the L, T primes, they just cancel. So I don't need to calculate. So the magnetic field is, let's see, mu 0 over 4 pi q proton over m r cubed times L. Yes. Now C is 1 over square root of mu 0 epsilon 0. So this is equal to 1 over 4 pi epsilon 0 q proton over mc squared r cubed times L. So now we also know B. Now we know the perturbation. H prime is equal to minus QE over 2m gyromagnetic ratio of E times S dot 1 over 4 pi epsilon 0 QP divided by MC squared R cubed L. There is one correction also to this one. Yeah, this is just a semi-classical treatment, 1 over 2. Now, that correction is not really a quantum mechanical effect. It's called the Thomas precession. The idea is, you see, we went to the reference frame of the electron. Well, the reference frame of the electron is not an inertial reference frame. So what we had done is not actually correct. If you do it the proper way, well, you have basically two alternatives. You can either say that, okay, at a given instant you go to a reference frame in which the electron is rest, but then you successively change your reference frame as the electron is moving. Well, those boosts, if you make the boosts, they amount to some kind of a rotation. That's what this precession is about. This is one thing to do. Another thing is you can just stay in the reference frame of the proton, which is at rest. Then, of course, there's only the electric field, there's no magnetic field. But then in this reference frame, the magnetic moment of the electron, it behaves like an electric dipole moment. So you have an electric dipole in an electric field, and So again, you get this correction with the correct factor of 1 over 2. Now, in electromagnetic course, did you see the Lorentz transformations of the electromagnetic fields? Okay, you will see them in your graduate studies in more detail. So just believe me, there is this factor of 2 correction. So this is our perturbation. If you write the charges, for GE is equal to 2, H prime is equal to minus E squared over 4 pi epsilon 0. One over 2 m r cubed. In fact, m. There is this 2 m squared c cubed r cubed s dot l. Now we need to calculate, now this is plus. Because the charges of the electron and proton are different. So there's a plus sign. There's an additional minus sign. So let's say this will come from an alpha. This is an order of the order of alpha correction. If you remember our relativistic correction also had such a behavior, m squared c cubed. So this behavior is also proportional to the relativistic correction. It's, in that sense, this is also included in the fine structure shifts. Now let's okay, the first thing we need to do is, we are doing degenerate perturbation theory because the states are degenerate. So is H prime diagonal in our basis? You see, up to now we were using the basis NLM. Now we didn't pay attention to the spin, but now we also have to pay attention to the spin. So there is also the spin part. We should also consider the spin part. Now, does H prime has non-zero matrix elements between states with different ms or m? So you see, we have degenerate perturbation theory. So we have to first diagonalize H prime, if it is not already diagonal. In the case of the relativistic correction, well, it was already diagonal because there was no operator, no spin or angular momentum operator appearing in our correction, so we didn't need to worry about diagonalizing our perturbation. Now we have this additional perturbation, but this perturbation, so we have to still pay attention to the fact that we are doing degenerate perturbation theory. So up to now we have been working with this basis. In this basis is H prime diagonal. So the matrix elements between states, degenerate states, are they zero for different states? So what do you think?
There's no overlap between the inertial velocities.
Okay, that's the definition of having non-zero matrix, zero matrix elements, but how can you see it? Straight by looking at this expression?
Doing this correction for different MS states with that dimension.
Yes, that's why it's degenerate perturbation theory. Now the question is, now we have problems in degenerate perturbation theory if this matrix element N, L, M, S, M, S, and let's say since we are doing degenerates, N, it should be the same M. Let's also put the same L and S, M prime ms prime. Can we say that this is 0 if m is not equal to m prime, ms is not equal to ms prime? So this is the question.
I guess S dot L becomes 0 in that case. It's only they become.
Do they? I don't know. Okay, you have 5 minutes during the break to try to remember some of your quantum mechanics and angular momentum.